All right, continuing on with class 14, here's yet another example. And I'm going to use one from Munson's fluid mechanics where it's a fan, right? So this is, we might have seen like a fan like this. Sometimes there's a fan in a motor that might look a little bit like this, where we are expelling air outwardly. It's a radial fan. And it's got a 12-inch outside diameter and a 10-inch inside diameter. And it's got a height of like 1 inch right here. So I'd like to actually probably be kind of neat for an example like this to get an example like this. So I got to be on the lookout for some small little piece. Actually, I could probably find this exact fan somewhere. I'll be on the lookout for that. If the flow rate is steady on a time average basis, it's going to produce 230 cubic feet per minute. And the absolute velocity of the air at the blade inlet is completely radial, right? So you could see, so they really make this. They can form this angle on purpose to try to make that as radial as possible, or that's just an assumption that we're making to make life easier. So the blade discharge angle is 30 degrees right there. So that's sort of like the shape of that angle from the tangential direction. The rotor rotates at a constant 1725 RPM, and we want to estimate the power required to run the fan. And these are some real world numbers here because that 1725 is an interesting thing. You know that we have 60 hertz electricity cycles, 60 cycle electricity in the United States. So the number of poles in your motor will contribute so that you'll always have like it'll be divisible by 60, right? But there's always going to be a little bit of slip. So this would be like 1800 RPM, except there's some slip in the motor, right? So it doesn't exactly go as it's being produced. So this is like that many motors you'll see there have something that's a little bit less than that number divisible by 60. I don't know, that just always jumps out at me. So anyway, we've also been included here, and Munson's using their own nomenclature here. You can see what is a velocity triangle, and we have to think our way. They've already done this for us, but a lot of times that's like some of the more difficult stuff to do is to try to picture this. And also, they didn't add to the e's because they have this over here, and they didn't put it on top of here. So let me try to explain the velocity triangle to start with. This is the outlet, right? So this is the velocity. Like if this thing was being held stationary and we were blowing air out of it, this would be the angle that would be coming out at right here, right? Probably actually something in between there, but this is what we're using right there. But this thing is rotating. So it's going to be rotating, and it's got that omega times this RPM is going to be in that direction right there. And that's what that U is, right? So that's going to be U, not a lowercase u, U2, not the band. So this thing is going to have a component that goes out in this direction, and that's going to be what we could call the normal direction or the radial direction, right? Because they mix up radial and the normal one. So you can see it's coming in at this velocity, and they're saying it's exiting at this velocity. And also, this also right here, by the way, has a tangential component, which would be, if we were going to draw it, be like in that direction right there. And you can see that this 30-degree angle is what they're saying they're setting this thing at. They're saying that forms a 30. By the way, people don't always use that angle, so you have to be on a lookout when people are giving you an angle, which one they mean. Sometimes they'll give you that complementary angle, so just be aware of that. But now you can kind of see this real velocity. This is the actual velocity V2 that's actually taking place, and so it's going to be, we're going to, by the way, they move this end to end because here is the actual velocity in the tangential direction, and so here is the radial direction. So here is the actual velocity that's taking place, right? So actually I shouldn't, it should be shorter because we should put that velocity right there, right? So that right there is the actual tangential velocity, because it's exiting here. I would call normally, and I don't mean to use normally, I would call this the radial personally. But it's going to have the same component in this, not really, the relative. I would call this the relative personally. But let's just stick with their lettering onto here, this designation. But right here is going to be the total V2 coming out. And it's going to be made up of what it shares the component. You can see it's the same component here in the radial direction. Hopefully that kind of gave you sort of an idea of what this velocity triangle, the ideas behind. But they're not the same, by the way, for like a fan versus a turbine, right? So just got to be, but it's underlying same principles, but not the identical approach to this because of the relative motions that are taking place. We also note that this is like a simplification. So there's something special about the volume flow rate as it relates to the radial direction. The radial direction really decides what that flow rate is going to be, but they gave us the flow rate, so we're fine. And with respect to that, we'll be able to go backwards and find what that velocity is going to be. So let me get the flow rate and turn that into, they had it as cubic feet per minute. Let's turn it into cubic feet per second, right? So that's just dividing by 60. So it's what, 3.833 cubic feet per second. I'm going to need the mass flow rate. And I'm going to go ahead and use, they didn't really tell us the temperature or the pressure. So let's just use atmospheric, what's given to us. And I'm going to use slugs. This textbook actually goes and uses it both in slugs and in pounds mass. I don't do pounds mass. So 2.38 e to minus 3. These are slugs per cubic feet. All right. So that's what we're going to use right here to get the mass flow rate. 2.38 e minus 3. Put the decimal, make it clear. And the 3.833 cubic feet per second. And that's going to give us, it's a small number, but it doesn't hurt. I like to use this little E designation because that's the way my calculator does things. It's also what Excel looks like, so I don't like going to the 10 raised to the whatevers. Okay, so there's some preliminary things. We could find out what U is going to be because we're given the RPM. So let me go with my angular velocity. I'm going to find my angular velocity first. I didn't do that before. Anyway, that's 1725. I didn't put the 1 in there. 2 pi, because that's radians per revolution, so that's going to turn. And then we also want to make it on a per second basis. So 1725, 2 times pi times 60 divided, and it's 180.6 radians per second. And let's see, anything else? Okay, I want U now. Let me get what we're calling U2 is just going to be the radius times the angular velocity. And we're given that, we're given the angular velocity, we know the radius, and this is going to be on the outside surface right here. So that's going to be 1/2 of the 12 inches. So we'll go 12 over 12 to get it into feet. 2 to make it into a radius, and 180.6, and we should get 90.32 feet per second. The equation for which triangle? Let's decide. I want to go V. Let's say it's this triangle, this big triangle right here. So that right there, noticeably, this is going to be W2 plus U2 is going to equal to V2, right? So let's write that out. Or just write V2 is equal to W2 plus U2, right? And once again, this is not always going to be a standard thing. You won't follow this exact example every time. It depends on the application, all right? It even depends on some of the ways the vane is shaped, because it might not be shaped that way. So just be aware. Okay, so let's go. I'm going to do in the y direction. And I can find my VR in here. So we're going to focus in on the y direction first. And my W, let me see, let me go the other way. So for one thing I know about it, I know the flow rate. And this is the total flow rate. And that flow rate is going to be exiting through a band, right? So I almost want to draw, let me draw it like this right here, right? It's going to be a band right here, and it's exiting that direction right there. So I want to get this area of that band. It's exiting in all directions right here. So that's going to be that velocity right here, that outward velocity. So let me go that V, I'll use their nomenclature, R2, the radial 2. That's going to be this divided by the circumference, which is going to be d2 times pi, right? That's the circumference around here, times the, did they give us a variable? They didn't give us a variable. What did I use? I decided to use h. And that's going to be the height of this, maybe, the height of that band. It's going to be this dimension right there as it's passing out. So we're going to say that we have 3.833 is our cubic feet per second. And the diameter is going to be, well, the diameter is 1, right? 1 foot, because it's 12 inches, times pi. And then we have 1/12 of the height of the thing to turn it into feet. And what we're left with, if we do this correctly, is we get 14.64 feet per second. Now that is also going to be equal to, right? That's also in this triangle. It's going to be the WR2, right? Because this thing is exiting out in that angle, so they're going to be equal to each other, right? That W and that there. So from that, we could figure out what W2 is going to be. W2, and we're going to take and divide by WR2 by the sine of that angle. So take 14.64 and divide by a sine of 30 degrees. So we get 29.28, right? Just makes sense. This is 0.5, so it's going to be 2 times the thing. That makes sense. And now continuing back to our velocity triangle to look up there, if you want to now get what this is going to be equal to, we can take the x direction. And the x direction of this equation right here is now going to be the radial. Okay, so this guy is entirely in the x direction. So what we're going to find, we're going to have v theta 2. That's this guy right here. So that's going to be the, call it a transverse direction, or we call it tangential. They're really pretty much the same thing here with the way we're talking about here. And that's going to be, in this case, let's not worry about the signs of the thing. The signs are dependent on what the triangle is right here, not dependent on this equation. And that's going to say that we're going to be, this is going to be, let's go say to the left, is the negative direction. So it's going to be a negative W2 times the cosine of 30. All right. Let me see the cosine of the angle. I'm going to write out it. Let's keep it as variables, and then we'll rewrite it out. And then add in U2, which is completely horizontal right there, right? So that's going to be a negative 29.28 times the cosine of 30 plus U2 is 90.32. And so the tangential direction is going to have a velocity of 64.96, and that's feet per second. All right, so that's the idea of the velocity triangles, is trying to find. And so the tangential is the only one that matters. So we can go to Euler's turbine formula. And that's going to see the torque, or the output torque, is going to be the mass flow times R2 times velocity 2 in the tangential direction, this guy right here, minus radius 1 times the velocity 1 in the tangential direction. So let's take the mass flow, which we found out is 9.123 E minus 3, and these are in slugs per second. And the radius is going to be 12 over 12 divided by 2. And the V we just found of 64.96 minus, we have the, we could do this, we don't have to, but this is going to be 10 over 12 divided by 2, right? Because that's the radius of the inside portion. But you'll notice this is completely in the radial direction, therefore there's no tangential. So what we're found with is the torque is going to be equal to 0.2963. And if you look at this, this is, by the way, I'll put this up to the side. These are slugs per second times feet per second. And so that's going to be what we could find. We could have a slug foot per second squared. So that turns into a pound feet, or foot pounds, as I like to call them. And therefore, we can find out what the power is going to be by taking the torque times the angular velocity, or 0.2963 times the radians per second that we found previously, which was up here somewhere. Did we find it? We found it right there, 180.6. And that's going to give us foot-pounds per second. We can divide by 550, and those are foot-pounds per second per horsepower, and get us into horsepower, and we're going to have 0.0973 horsepower. So this is the power required to be able to do this. But remember, if we needed electrical power, we would need to divide this by the motor efficiency in order to operate. But actually, to tell you the truth, before we did that, we would need to divide by the efficiency of this fan, because this is going to be inefficient. There's going to be all kinds of losses. For one thing, notice we're pretending as if there's like a plate right here. There is no plate right there. So there's going to be like air that escapes out of the top of this right here. So that's one aspect of it. It's also going to have some just natural losses. I'd say, air isn't that viscous, but it does have some amount of viscosity, which is going to have like just inherent, like the turbulence and that type of thing is going to end up causing like friction losses, and it's going to heat up the air a little bit because of that. We don't really have to worry if you just look at the speeds. These are much lower than the speed of sound, so that's not a issue or a problem, right? These magnitudes of these speeds. There's a bunch of assumptions going on here. So this would be an inefficient fan, and in terms of the torque that would need to be able to accomplish this. So we would divide this by the fan efficiency, and then we would once again divide it by the motor efficiency to get the electrical power. So I like this example. It took a long time. That was actually 19 minutes. I'm kind of surprised that it took me that long, but it's an introduction to velocity triangles.